Hey, welcome back to another video on large language models. In the last couple of weeks where I've put out videos on langchain, one question that came up quite a bit was about this idea of using embeddings, and there have been questions around tools like Chroma and what does it mean to be generating or storing embeddings. Like this whole process feels a little bit opaque from the outside. Because langchain and LlamaIndex, these kind of higher level frameworks, they abstract away quite a bit of complexity and they help you be productive with LLMs, but at the expense of really understanding what's going on behind the scenes. This video and the next few videos I'm releasing will explore on a deeper level what makes LLMs work and what powers the tools you love like langchain and LlamaIndex, and what happens when you use a natural language query to query your CSV, your database files on private Excel spreadsheets, etc. This video, our focus is on the embeddings and we'll tackle the other topics in the next few videos. So to really understand this concept, we'll begin by using LlamaIndex to generate some embeddings, and then we perform a Q&A, question and answer on some internal documents of text. We then start to peel off the layers, we swap in Chroma, and we start to inspect what really happens with these embeddings and how they generate it. Now you can compare the result of the Q&A with the embeddings generated through this method using Chroma to the first video we did in this series, and you should expect to see a higher quality result depending on how you set up Chroma embedding, but I'll comment on that later as we code along in this video. So let's open up everyone's favorite editor and let's create an empty file and let's get started. So I'm gonna go ahead and say demo6.py, we're already on 6. And of course, if you want to follow along from demo 1 to demo 5, all of the code, all of the sample data set, as with the rest of the series, all of them are available on GitHub and on my YouTube channel. So for this demo, I'm going to be using LlamaIndex. So I'm going to go ahead and say from LlamaIndex import. So I'm going to say GPT simple vector index. Okay. If you're trying to code along, you should have LlamaIndex as a dependency as well. If you don't know what that is, go to my GitHub repository, find the repository, and then do a git clone, and then do a pip install -r requirements.txt. It's going to install all of the dependency in the requirements, and then you can hop back in here and code along with me, right? Now, the GPT simple vector index is a data structure where the nodes are keyed by embeddings, and those embeddings are stored within a simple dictionary. And during query, the index will use this dictionary to query for the top n amount or top k amount, most similar nodes, and then it synthesizes an answer from the retrieved nodes. So if you have a lot of documents, right, you have a lot of nodes, you will have to figure out which are the most similar nodes, and then you have to synthesize an answer from that. I will comment more on that later. I'll talk about how it actually finds this notion of similarity. What does this mean, and we talk about semantic search. I'll talk about that as well. But right now we're going to say GPT simple vector index, and I'm going to have a directory reader because I have my files, all of these files in the directory called news. So I'm going to have to use the directory reader to read the text that I have in this directory. Alright, so as usual, I also want to load in my environment keys. So I'm going to say from load.env import load.env, and then I want to just make load.env, and that what this is going to do is to just look for my env file and going to pull in everything that is in the env file. So that includes my OpenAI key, that includes, I don't know, my Elasticsearch key, whatever I'm using, right? So now you need some documents to work with. And I just told you that my documents are stored in the news directory. It means you could just read them in by using the simple directory reader, and the name of the directory is news, so let's call it news, and let's just say load data, and that's it. One line of code and you just loaded in your text from the news directory. The documents itself is not enough, we need an index. So let's go ahead and create an index, and this is just the simple GPT, and you say from documents and you pass in the name, and because we name it documents here, I just pass it documents. Now you could go ahead and just start to do this query already, but I also want to save this to this. I want to save this index to this, so I'm going to go ahead and say index dot save to this. You see there is a save to dict, this save it as a dictionary. This method stores the index into a JSON string, but I want to be using the save to this because I actually want it to appear in here, and I can commit that to Git as well. You can compare that. Okay, so I'm going to say save to this, and I give it a name here. I'm going to just call it index.json. Okay, you can maybe name it simple index.json. This is entirely up to you, right? Once I have that, I could ask my query. I could say something like index.query, and this is the result. So I'm going to, in this case here, I'm going to ask a simple question. This is relating to the coal mining industry, so I'm going to ask questions relating to that. And my question would be, who are the main exporters of coal to China? I live in Indonesia, and a lot of my clients are in Indonesia, so I want to actually add another part of this question, the two-part question this is. So the second part of the question is that what is the role of Indonesia in this, right? So who are the main exporters of coal to China? What is the role of Indonesia in this? I could just print the result. I don't really need to do anything else, just print the result. That's it. So how many lines of code is that? 1, 2, 3, 4, 5 lines of code without counting the imports. You have that. So let's just run it. Activate the environment, clear my screen, bring it up a bit so you can see it. Then I can now say Python demo6.py. So the answer came back and it says the main exporters of coal to China are Indonesia, Russia and Mongolia. Indonesia is the largest exporter of coal to China, accounting for 58.3% of total imports. Mongolia is expected to export approximately 40 to 50 million tons of coking coal to China in 2022, making it the largest coking coal seller to China for third consecutive year after it replaced Australia in 2021. So today we're already in 2023, so this is not very updated information, so we should have to update that in the news directory, but let's put that aside for a bit. We see how it works now. And because we did save to this, you should also expect to find a simple index.json. If I click on that, you should see the embeddings in here, right? So these are the documents, and each of the sentences in each document would have its own embeddings, because so if you look into result.txt, for example, right, these are the different summary, these are the different sentences. And if you look at summary.txt, this is again, all of them are different sentences. So if you look into what happens in simple index.json, it's creating this embedding for you for each of the sentence, and it's doing this like embedding stick, storing everything in a JSON file for you. And that is really what all of these LLM tools is relying to make it work, right? It's trying to find, okay, out of all of this, to answer this question of like, who are the main exporters of coal to China? Well, there is so many different information in here, which is the right document to look for, and which is the sentence that may contain the answer to it. And then you have to bring those sentences in and then synthesize an answer using all of these different sentences. And the answer may lie in multiple different sentences. You may not get the answer by reading on just one sentence. You may have to read them through multiple sentences. So each of the sentences have these embeddings, right? So basically, each of the sentences have a numerical representation of this sentence. This numerical representation contains the semantic similarity. So if this sentence sounds very similar to this sentence, if they're describing the same thing, you would expect them to be semantically similar to each other, and therefore the numeric representation of that should reflect that similarity. Okay, so let's close that out. I want to mention that since you know how to save to this, you should also learn how to write to this, or how to load from this. And loading from this, suppose we don't want this anymore, we could hide this out, and we could also just comment this out. Suppose I already have this saved to this and it's called simple index.json, then I could just go ahead and just load it in by doing the same thing, GPT simple vector index, and instead of save to this, I'm gonna have load from disk and just give it a name. So in this case here, we name it simple index.json. So let's do it like this, and let's save it. So this is gonna save you some token as well, and this is gonna save you some money, save you some time, because you're no longer trying to build the index using GPT. Instead, you're just gonna load it from here, and you're gonna ask a question. So it's gonna save you some time, save you some money, save you some costs. It's good, right? So you can save the index this way, and then you can load the index by using the load from this method. Duplicate the demo6. I'm going to rename it to demo7. And now I'm actually going to go into Chroma. I'm going to talk about Chroma. I'm going to keep some of this, and I'm going to remove some of this. I would remove both of this. I will keep the rest. I will also replace GPT simple vector index. We'll replace that with GPT Chroma index. I'll talk about why that is. Now earlier I mentioned that the GPT simple vector index is stored its embeddings in a simple dictionary, right? It has its advantages as well as its disadvantages. So the advantage is that it's fast to build, it's just a simple dictionary, it doesn't need much more than that, right? It's easy to implement. But compared to a dedicated Chroma index, a Chroma collection, it won't be as fast or efficient to query, or even as robust, because a simple vector index is really just a dictionary. The GPT Chroma index, it creates and stores these embeddings within the Chroma collection. And then during index construction, this document text, the document texts are going to be chunked up, they're going to be converted to nodes with text, and then they're going to be encoded in document embeddings stored within Chroma. And then during the query time, when you want to query, right, the index will use Chroma to query for the top K, top N, most similar nodes, and then it synthesizes an answer from that. And I did mention about Chroma. In fact, I'm going to show you the example again. This is the website. It says it is the open source embedding database. It makes it easy to build LLM apps by making knowledge, facts, and skills pluggable for LLMs. Right, so you have your queries. You can use OpenAI, you can use anything else, right, to generate the embeddings for it, but then you need to store it. So you need to store the documents and the embeddings, and you can, of course, once you have this stored, you can reuse this. You don't have to keep calling the GPT embedding anymore, right? So you can, again, save some money here. Then you can use this to create the LLM context window so that your GPT or LLM will be able to answer the question using the context window that was created from this step. Right? So give you the tools to store embeddings in the metadata, and embed documents and queries, and insert embeddings. So in fact, I have another notebook running up here to show you some example. To create a collection, you say Chroma.client, and then you say client.create collection, give it a name, right? You can name it anything. Here it names it test. You can name it something else if you want to. And then once you have the collection, you give this is assigned to a variable called collection. So you can use that collection to add embeddings. So in this case here, we add 8 different, think of them as sentences, 8 different sentences. Each sentence have a embedding, and the dimensional space is just 3, so just 3-dimensional space, right? So the first sentence, it's going to be embedded to this numerical representation of 1.1, 2.3, 3.2. And then the second sentence, 4.5, 6.9, 4.4, so on and so forth. Altogether, there are 8 of them. So you also want to have the metadata. If you choose to, you can also have no metadata, it's up to you. And then documents, these are the 8 different documents. So again, each document refers to, maybe think of them as one sentence, think of them as one paragraph, or what have you. Once you've done this is in the collection.add step, okay? Once you have done that, you could do the query step. And the query step basically says this. It says, okay, find me the query embedding. Which of this document, let's say we have Harry Potter part 1 to part 8, right? And I asked a question about Harry Potter, who is Harry Potter's first kiss, right? Now, instead of having to get GPT to read through all 8 books of Harry Potter, that's a lot of books to read. That's, I don't know, hundreds and thousands of pages to read. Instead of doing that, what you're trying to do is to say, wait, maybe if I ask the question of like, who is Harry Potter's first kiss, maybe you shouldn't have to look at all of the 8 books. Maybe what you need to do is to find the books where Harry Potter is mentioned along with the girlfriend, which means, which in this, I don't know, Ginny or something? Ginny, maybe, right? It finds the word Harry Potter, it finds the word Ginny, and maybe it finds the word kiss. And it says, okay, does this kind of, does any of these 8 books, right, contains any notion that may be a hint to where the answer may lay, right? So maybe, for example, simplistically, you can think of it like, out of the 8 books, the first book, so Ginny wasn't even introduced as a character in the first book, so it's out of the question. Second book, third book, okay, the 5th book actually mentioned about Harry Potter, mentioned about Ginny, Ginny Weasley, I think his name. I don't know. I may have mispronounced her name. It also contains the word kiss in a few pages of that book, book 5, right? So it tried to create this context window and say, well, the answer may lay in book 5. So in this case here, it says 1.1, 2.3, and 3.2. Now, which one of these documents here are the most similar to this? So it turns out it's ID number 1. So that's ID 1, because ID 1 here is exactly 1.1, 2.3, 3.2, right? So that's number 1, and as well as 5. 1, 2, 3, 4, 5. This is also exactly the same. And so it returns ID 1 and ID 5. Why? Because you asked it to return 2 of them, right? Then it looks like the second one, 5.1, 4.3, 2.2. It says, okay, which of the documents here contain the hint, contain the clue to answering this question? So for example, when did Voldemort hold hands with Harry Potter, for example, right? So again, you have to find out, right, out of the 8 different books, there may be which of the book is the most relevant into answering the question. In the Harry Potter world, it may be book 8, right? But in this case here, it turns out that the answer will be ID 2, the book number 2, and book number 4, because they are, if you were to do the numeric in here, you can use Euclidean distance, you can use any kind of similarity, cosine distance, whatever. And you compute the distance, you will find that the book ID number 2 and book number ID number 4 would be the most closest to this in that vector space. So that is how you do a query, right? You say that instead of, if I ask a question about Harry Potter, you don't have to go and scan through all the 8 different books. In fact, passing on 8 different books to something like OpenAI GPT is probably going to be problematic. There is a maximum prompt limit, and you will far exceed that already, even before the first book ends, right? So it's not feasible, it's not useful. So what you want to do instead is to basically find the right chunks and say, hey, I take all the 8 books and I put them into 100 chunks, and turns out you don't need to look at all the 100 chunks, you only need to look at chunks number 64 and chunk number 69, and the answer contained within these 2 chunks. That would be much more manageable and it's much more feasible, right, when you come to implementing LLMs. We did see from the website, it says that you just have to call the client and then call create collection. That's all you need to do. So it's very similar here when we use LlamaIndex. We just have to create a client and then we just have to create collection. So let's go ahead and do that. So Chroma client, and we say import ChromaDB, and it will be on this API, it will be exposed here, ChromaDB.client. Alright, we go back to the documentation, and it says that once you have the client, you want to just say create collection and give it a name, then you can add and then you can query. Alright, that sounds simple enough. So let's go ahead and do the create collection. Maybe add a bit of comment here, say create a collection here. Chroma collection equals to Chroma client create collection. This is exactly what the docs tell us to do. You can give it a name. I'm going to call it news pieces because they're kind of news And that's about it. That's all you need to do for Chroma. Right, so this is in the usage guide. You can see how you use collections. It lets you manage collections of embeddings. There are a few restrictions that you need to be aware of. The length of the name must be between 363 characters. Once you get the collection, you can delete the collection. You can do a peak count modify. So there's a lot of things you can do here. I'm gonna go through each one of them. But this is a nice database. You know, they has this kind of like ORM experience where you can just query, you can get, you can delete, you can pick. So for example of this counts, return number of items in the collection, and then there's the pick. Alright, so let's actually implement some of this. I want to start off by saying here, just do a print Chroma collection, and I want to just print the count. I should expect 0 because I haven't really loaded anything in it. I'm just creating a collection, but it's an empty collection. And then I'm going to load the data in here. My print, I could maybe just copy this down. Now I should expect to have at least 2 because there are 2 of them, but maybe it chunks it up to even more of them. But okay, there should be at least 2 here. And now I can actually create my index. So the index tab is similar to what you have earlier, GPT Chroma Index, from documents, pass in documents, but this time I also want to say this is the Chroma collection, and that refers to my Chroma collection because I name it Chroma collection. If you want to save a copy of this as well, you could say index.save to disk, just like what I showed you earlier. I would say news pieces.json. Alright, so when I run this, it should hopefully create a JSON file for me as well, and it will contain that information about this index. So what do? We create a collection. We print the collection to expect, this should expect 0. Right, expect 0. Then we're gonna read in the data. This is very simple. We've done this before earlier. And then we just say, okay, from here, this is the list of documents to create the index from, to build the index from. So this is the list of documents we're passing here. We say, using this document, using this collection, this store, right, go ahead and create our index. And then finally print that out. So let me go ahead and say python-i demo7.py. Run it, everything. Let's make sure everything is working. So everything is working. Bring it up. Alright, so let's take a look. The final result is still the same, right? The main exporters of coal to China are Indonesia, Russia, and Mongolia. Indonesia is the largest coal exporter to China, accounting for 58.3% of total imports. Mongolia is expected to... Okay, so we read this before. But now that we're in interactive mode, we get to print the inner workings of our embedding databases, our index store, we get to print the results, we just get a better picture of what's going on under the hood. So let's go ahead and inspect each one of them, right? So we start off with this R, and we work backwards. So we start off with R, we said, who are the main exporters of coal to China, and what is the role of Indonesia in that? Alright, now if I show you what happens with R, let me just print R, it's going to come up with this, right? It's going to come up with this chunk of text. It says, this is the response. Look at what happened here. It gave you these source nodes. It's telling you that, hey, I'm going to go and look up the right nodes because it's going to try and, remember the Harry Potter example? It's going to try and build hundreds of nodes, right? Because each question that you ask, you don't have to scan the whole Harry Potter series from book 1 to book 8. You only need to scan the relevant nodes that contain the information. Who did Harry Potter kiss first in the book, right? Who was his first kiss? In fact, now that I think of it, I don't think it's Ginny. I think it's Cho Chang or someone. Alright, so I don't know. It may be a spoiler. If you haven't read Harry Potter, well, the spoiler is that his first kiss wasn't Ginny Weasley. It was Cho Chang. And it tells you that, hey, I didn't need to look at all of that. I just need to look at these relevant nodes. And it gives you all of that information. And then it gives you the relationship. And it points out this one. I want to print this out because this is quite useful. I'm going to copy this. And I'm going to say, this is what we get from R. Let's print that out. So this is the score. This is kind of like what we see in the earlier example in the Google Colab. I showed you a score. A perfect score is that there is a perfect answer to that. It was right in there in the same dimension. It's very unlikely. So you want the score to be high enough, but it's not going to be 1, right? Unlikely to be that. We get back up here. We see this is the index.query. So it would also be nice to look at the index itself. So let's go ahead and print the index. And we print the document store. Because remember, we have multiple documents. Well, in this case here, I'll make it simple by having 2 documents because I don't want to use too much documents and then cost a lot of money. I'm going to use 2 documents. So just going to print the document store. And it gives you this information. Let's also copy this up and also add this. This is getting interesting. So what do we have? We have the first one. This is the doc hash. Then we have the second one. And then this is the doc hash. It says that, well, out of 10 different books, only the second book contained answer to that question. So when you look at the node that is trying to look up, this is the CEBC, this is the CEBC, right? So it's saying that, hey, instead of having to look through all of this, no, you only need to look at the second one. The answer lay in that. The answer lay in that, alright? So that is what you get from the doc store. And remember how in the documentation, you see that there is the peak. This returns a list of the first 10 items in the collection. Well, this is what we want as well. Let's take a peek of that. So what did I name my Chroma collection? I name it Chroma collection, perfect. So I'm gonna go ahead and say Chroma collection dot peak. You see different documents. So it has the document 1, 80509948. That's the first one here. And then there is a second one here, which is CEBC554D, CEBC554D. So this peak prints the first 10 items in the collection, and then it tells you, okay, these are the documents in here, and this will show you the inner workings of its retrieval process. So now in this case, if you have like, let's maybe not using the Harry Potter example, maybe you just use a corporate world example, okay? So let's say you have 500 documents, maybe annual reports, maybe earnings reports, and when you issue a query asking what is the operating income of this company in 2015 or 2016, whatever, or how much did R&D increase by this quarter, right? Now the job is to first identify which among these 500 documents, where we have 500 documents, all kind of reports, earnings reports, annual reports, which among these 500 documents is the most relevant, right? Are the most relevant to the query, and then to extract the answer from that document. Okay, so this selection process, this retrieval process relies, of course, on the idea of embeddings. And in earlier videos, right, when we talk about embeddings, we always using this OpenAI's GPT method to do the embeddings. So OpenAI also have this embeddings as a service kind of, right? You can just send the data in, GPT is going to take that and then generate embeddings for you. So Chroma does provide a convenient wrapper around OpenAI's embedding API, right? This allows you to call it with your API key, you pass in a model name, it will do that. But OpenAI, by default, it will use this sentence transformers, and that's good. It's good because it's free, it's open source, and it's actually really fast as well. And it also has the benefit of not having to send your data up to OpenAI server all the time, because every time you have data and you say, oh, I want to create an embedding, you have to send the entire data over to OpenAI server. If you work in a company, there may be problems with that. You can't just just take data and just keep sending over to OpenAI. It's fine if you want to send some sort of query and you say translate that to SQL. I think that's okay, provided that your query is generic enough, right? You say that, hey, I have this question about my database, please convert this to the right SQL, right? That's fine. SQL statement, that's fine. But sending your entire data to do some sort of embedding, that sounds a bit more risky. So in this case here, right, we're using this embeddings method here, and this has the benefit of not having to send data up to OpenAI server, because the embedding function runs completely on your computer, right, instead of running this remotely on the OpenAI server. So a lot of benefits, right? It runs in memory, it's free, it's open source, and it's actually quite fast. In my personal experience using it for a bunch of different data sets, it just works. And as a bonus, you can also add a persist directory to persist and read them from that directory back later. And these embeddings are actually quite small, so you can store them on this, you can store them on your computer, and you can read them back in later. Now I'm going to go through this a bit, right? It says here it provides some lightweight wrapper, but the default is to use sentence transformer to create embeddings. So I'm going to actually go and find this all mini LM L6v2. So I'm going to do a quick search on that, and we will search that up on Hugging Face. And this is the model. This is a sentence transformers model. It maps sentences and paragraph to a 384 dimensional space, vector space, and can be used for tasks like clustering and semantic search. Now I'm going to go ahead and just do the sentence transformer to show you what is actually happening when you call it with Chroma. So let's go ahead, from sentence transformers, import sentence transformer. Right? Then we give it a model. Now there are many different models you can use, but the one that Chroma is using is this all mini LM L6v2. Alright, so we're gonna actually use the same one here. So we'll say sentence transformer, pass in the name L6v2. Okay, and it's using my CUDA device, my GPU, which is great because then it's fast, runs it on GPU. Now let's give it 4 sentences, 3 sentences, whatever, right? So let's just say sentences. Let's add a few sentences here. I'm going to say that this framework generates embeddings. So when I say this framework, I mean the sentence transformer generates embeddings for each sentence, right? I want to say this is not words. Okay, this is sentences. So make a note of that. Each sentence will be encoded or mapped, right, to a 384 dimensional space. Right? So what it means is that each sentence will be transformed into these 384 numerical numbers. That's the second sentence. The third one is just something simple. Let's just create something like supertype.ai helps companies productionize the machine learning systems. And let's do the fourth one. I want the third one and the fourth one to come to be quite similar in terms of dimension. So I want to maybe have my supertype.ai is my first company, and I have a second company called algorithm.ma. So that maybe helps companies train and upskill their data science team. Right. So ideally the third and the fourth sentence should come very similar to each other, because they would have their embeddings, the resulting embeddings will come closer to each other than the first and the second sentence. Then you can create the embeddings. Say model.encode sentences. Right? And it does it in one batch, because these are 4 sentences. This is not the Harry Potter book. If you actually have a massive amount of document, then it would be far longer. This is, I don't know, this is nothing. This is not even a second, right? This is really, really fast, all right? Now we can just print embeddings if you want. So you can say something like 4 sentence, do a for loop, 4 sentence embedding in, and you can zip them. You can say sentences, embeddings, and you can just print them out. So you can say print what? Print the sentence, and print out the sentence here. Then you can do the same thing here for embeddings. And what you want to print embedding. I name it embedding, so I want to make sure I don't put embeddings there. So put embedding. Maybe this should be removed. I can print an extra space. I can print I think this will work. Then I just print a new line. Just run everything. Okay, this is 384, right? From here all the way down here, if you were to do a length and just count them, you will see that it's 384, right? So it takes the sentence, like algorithm helps companies train and upskill the data science team. You take this sentence and convert that to a 384 dimensional vector. And here as well, it takes the sentence, supertype.ai helps companies productionize their machine learning systems. It takes this sentence and again it converts that to a 384 dimensional vector. And then you can compute the similarity. You can say, okay, which one is the most similar? Which one was the difference between them? So when you issue a query and you say, well, who are the main exporters of code to China, instead of having to look through all of the documents, it finds, okay, which of this contain the most relevant piece of information, right? Relevant in terms of answering this question, right? Which one of them? And then it figures that out, and then it looks at that node, right? Find that node, then it use that node to then generate context, then use the context combined with your query, pass it to an LLM. The LLM would then consider them along with the history. If you have some sort of chatting bot and there is some historical prompt, it would also consider that. So you can ask follow-up question. You say, okay, that's good. Give me a breakdown. Okay, that's good. What about next year? You can ask, and it keeps the history into the context as well. It keeps this into the context as well, and then it generates the response using the context they provide, right? So let's maybe summarize this a bit. We did cover quite a lot. In particular, we get to see LlamaIndex in action, and there are a lot of overlaps between LlamaIndex and langchain. I would say the langchain is maybe more of a framework and does more out of the box, where LlamaIndex, which formally is named GPT Index, I believe, right? It's created to focus on the indexing aspects of LLMs. So it really started off as this interface, right, where you can take unstructured data and then generate embeddings for it, and then give it some structure, and you can then query it. So of course, both of this, langchain and LlamaIndex, both have evolved over time, and they have a lot of new features and being added to it all the time. So I'll say learn both of them. Chroma, we spent quite a lot of time on it as well. It's an embedding database, right? We saw how it can be used to store embeddings and how that matters in the case of semantic search. And Chroma is a very popular option in both langchain and LlamaIndex. It's typically used with this GPT Chroma index, which combine to help you create a large corpus of text, turning them into some numerical representation that encapsulate a certain semantic meaning. So when the user needs to query with natural language, we can use these embeddings, the ones that you see here, can use these embeddings to look up only the document that are relevant to the query and then present that information to GPT to generate the response. This is the context window, right? And so that's it for the video. I hope you enjoyed. If you want to learn more about LLMs, you want to learn more about langchain, LlamaIndex, check out the rest of the videos in the series. Let me know in the comment section if you want to follow along and you have questions or ideas for what you want to see next. I hope you have a great day. See you in the next video. Bye.